Hello everyone, I am Shankar, Control Systems and Power Electronics faculty at Ohm Institute. So, in this video, I would like to explain some of the applications of Laplace transform. Not some, I just focus on one particular concept. So, why? Because in the recent exam AEE paper conducted by TSPSC, there are 4 to 5 questions came from Laplace transform concept. Of course, this is very basic concept for electrical engineering. It not necessarily to mention whether it is in the syllabus or not. So, what's the point here? Because most of the cases in electrical engineering, whether it is a circuit analysis or power electronics analysis or some other concept, basically the circuit modeling point of view, the components involved in any electric circuit, resistance, inductance and capacitance. By simply writing the basic equations here, it involves differentiation and integrations. By solving such differential and integral equation in a time domain, it is a somewhat time consuming process. One of the easiest method is to solve such equations by taking Laplace transform. Of course, we will not go with all aspects of the Laplace transform, especially even in the Laplace transform again, sometimes some transfer function will be given and how to find the solution of it by using inverse Laplace transform. So, in this short video, I will take one problem and then I will explain how to apply inverse Laplace transform concept in order to solve these particular equations. Now, I took one problem here, let me read here. If f of s, that means Laplace transform of a system, some system is given as 3 by s into s square plus 2s plus 5, then find f of t. Okay. So, in this particular case, Laplace transform of certain system is given, we need to find out what is the solution of that, that is a function value in time domain. So, if it is directly in the standard form, you can directly apply what is some inverse Laplace transform and you can do it. But in this case, observe carefully here, its denominator is expressed as the product of two polynomials. One is s, another is s square plus 2s plus 5. Again, by closely observing this second order polynomial, it cannot be factorized because the roots of this polynomial are not the real numbers, they are the complex numbers. Whenever roots of the denominator polynomial are the complex numbers, there is a different procedure. See, the reason in selecting this particular problem is mostly students will face a difficulty to solve this particular problem. Now, let us see here. When the roots of the denominator polynomial are the complex numbers, how to express in the partial fractions? First, let me write down given function 3 by s into s square plus 2s plus 5. Okay. So, the denominator roots are complex numbers. How can you identify? Simply can calculate b square minus 4ac. b square is 4 minus 4ac, that is 20. So, b square minus 4ac is a negative. Therefore, if you write down the expansion, roots expansion minus b plus or minus root of b square minus 4ac divided by 2a. So, inside a root b square minus 4ac is a negative value, hence the roots will be the complex numbers. When you concluded the roots are the complex numbers, you can express the partial fractions like this: k1 by s plus k2s plus k3 divided by the given polynomial. So, the overall function is expressed as a sum of two terms. In this, it is expressed as a partial fraction coefficients by using this form. Okay. Once you got that one, let us take LCM in the denominator, s into s square plus 2s plus 5. Therefore, what I can have here, k1 into s square plus 2s plus 5. Now the second term, k2 into s square plus k3 into s. So once you got that form, left hand side this is normal. Compare the coefficients. Compare the coefficients. Okay. So first let us compare constants on both sides. Okay. So what are the constants in the left hand side? That is 3. Numerator, denominators are same, so you just focus in the numerator part. Left hand side constant is 3, right hand side 5 into k1. Therefore k1 is equal to 3 by 5. That is the first coefficient. Next one, let us look into s square coefficient. Of course left side we don't have any s square coefficient, take it 0. Now the right hand side s square coefficient, here k1, here k2. So k1 plus k2 is equal to 0. Therefore k2 is equal to minus k1 and it will give you minus 3 by 5. Next, s power 1 coefficient. Again left hand side there is no s power 1 coefficient and hence I can take it 0. And the right hand side, what is s power 1 coefficient? 2k1 plus k3. Therefore k3 is equal to minus 2k1. Hence I can write here k1 is equal to, k3 is equal to minus 6 by 5. So these are the coefficients. Okay, if you have multiple problems practice, you can able to directly write down these coefficients also. Okay, once you got these coefficients, now let us rewrite the given equation. What is that? F of s is equal to k1. Okay, let me write down just for clarity once again. K1 by s plus k2s plus k3 divided by s square plus 2s plus 5. S square plus 2s plus 5. So k1 is 3 by 5. So I can write down here 3 by 5 in the numerator plus s. Divided by s plus k2 is minus 3 by 5, k3 is minus 6 by 5. Therefore minus 3 by 5s minus 6 by 5 divided by s square plus 2s plus 5. Okay. Now just let us simplify further. 3 by 5 into 1 by s, first term, minus from the second term, say for example, if I take minus 3 by 5 common, then what we will have? S plus 2 divided by s square plus 2s plus 5. Okay, I hope you are following. S plus 2 divided by s square plus 2s plus 5, right? Now let us further simplify this. 3 by 5s minus 3 by 5. Now follow carefully here. Denominator, I would like to write it in the form of a plus b whole square. How can I write? S square plus 2 into s into 2 into s into, let me write 1 by 1. Of course, it is a 1 only. You can simply write 1 also, nothing wrong in that. But if you follow this format in the any different models also, it will be easy. So what is the point here? I want 2 here, s into some number, right? Plus this 5, how can I write down? 1 plus 4. Instead of 4, let me write it as 2 square. Now if you observe carefully here, this particular part, you can simply write it as s plus 1 whole square plus 2 square. Therefore, numerator, how can I write down? S plus 1 plus 1. S plus 1 plus 1. Now, let us further rearrange these terms. 3 by 5 denominator s minus 3 by 5. How can I write down numerator? S plus 1 divided by s plus 1 whole square plus 2 square plus 1 divided by, again the same denominator, s plus 1 whole square plus 2 square. Okay. So what is the reason to write it in this form? Say for example, if you just look into this Laplace transform, formula here, suppose Laplace transform of e power minus at sin omega t. How can I write down this one? A by I'm sorry, omega divided by s plus a whole square plus omega square. Similarly, Laplace transform of e power minus at cos omega t. What is this one? S plus a divided by s plus a whole square plus omega square, right? Now, if you just observe these formats, s plus 1 divided by s plus 1 whole square plus 2 square, that means it is in the second form. So I can take inverse Laplace transform for this one as a simply cos function. But here this 2 is not there, so simply I can modify by multiplying with the 2 and dividing with the 2 also. Nothing wrong in that. Therefore, if you write down inverse Laplace transform, so till now this is f of s. Now if you write f of t, how can you get f of t? By taking inverse Laplace transform. So what is inverse Laplace transform for this first term? 3 by 5 into inverse Laplace transform for 1 by s. That will give you 1 minus 3 by 5 into, so what is this? E power minus t cos 2t, okay, plus. Now if I take 1 by 2 outside, then it is in the form of the first one. Therefore, I can say the inverse Laplace transform will be e power minus t sin 2t. So, this is a inverse Laplace transform. Okay, so you can stop with this. So, this is the answer for the given f of s. But in the generalized format, going forward, that means in the time response analysis of a second order system, particularly this concept will be used. So, I would like to modify this one just from the application point of view. Let me rewrite this equation once again. What we got, f of t is equal to 3 by 5 minus 3 by 5 into e power minus t. I took it out from these two terms. Then what we have, cos 2t here plus 1 by 2 sin 2t, right? So, this is what f of t we have. Now, instead of stopping with this, what I would like to write, I would like to write down this particular form as some constant multiplied with cos of certain function. So, for example, say here, let me treat it like this, a into cos omega t plus b into sin omega t. Okay. So, this particular expression can be rearranged like this. Suppose if I divide this with root of a square plus b square, this term also root of a square plus b square. You cannot divide in this way like this, therefore, I will multiply it, root of a square plus b square, right? Now, this particular term, I would like to call it as cos phi. Similarly, this particular term, I would like to call it sin phi. Therefore, now this overall expression, what I can write down? Some multiplying factor a square plus b square into, if you read it properly, cos omega t into cos phi plus sin omega t into sin phi. This can be written as cos of omega t minus phi. That can be written as cos of omega t minus phi. Now, I am going to apply this particular concept to the previous one. So, see, this is some generalized expression. Let me put it in a box here. Now, f of t, how can I write it down? This f of t is equal to 3 by 5 minus 3 by 5 into root of a square plus b square, root of, what is a here? 1 plus b square, that is 1 by 4 into e power minus t, multiplied with cos of omega t, that is 2t minus phi. We will define what is phi here. So, 3 by 5 minus 3 by 5 into root 5 divided by root 4, that is 2 into e power minus t cos of 2t minus, now let us see what is phi here. In this case, where phi is equal to tan inverse sin by cos, then tan inverse tan phi, it will give you phi. So phi is equal to tan inverse b by a, right? So what is phi? If you apply that formula here, phi is equal to tan inverse b by a, where a is 1, so b is 1 by 2. So tan inverse 1 by 2, this is approximately 56 degree. So I can say this is 56 degree. If you want, you can further simplify, or you can just leave it like this. So this is f of t. So this is the final answer. Now, of course, mathematically this is okay, but what this equation is telling. Now let us look into a little deeper. So with this, mathematically the solution is over. But how this particular equation will be useful to interpret our control systems? Now let me write down this solution here. What we got? F of t is equal to 3 by 5 minus 3 by, I can say 2 root 5, 3 by 2 root 5 into cos of 2t minus 56 degree. So this is the solution. Say for example, now if you see the original function, if I consider that f of s is the transfer function of a particular system, okay, say for example, let me take it in this way. This is transfer function of a system, right? What is the transfer function here? 3 by s square plus 2s plus 5. Okay. Now for this particular system, some unit step function is given. Now let us say this is f of t or f of s, correct? So what is f of s here? 3 by s into s square plus 2s plus 5. Now if you see the roots of the system transfer function, you will notice here the roots are placed at this point. Okay, minus 1 plus or minus j2. So the location of these complex roots having real part of minus 1, imaginary part plus j2 minus j2. Now I am sorry, here there is a one term is missed. In this case e power minus t is also there, e power minus t. Now if you observe carefully, in this response, time response, there are two terms. One is exponentially decaying term, e power minus t. That exponential decay is the same as real part of the pole. Exponential decay is the same as the real part of the pole, and it is having certain frequency, certain oscillations. Okay, so the frequency of that oscillations is given by 2 radian per second. So in a simple terms, what I can say that response has exponential decay and sinusoidal oscillations. Sinusoidal oscillations. This exponential decay decided by real part of the system pole. Sinusoidal oscillations whose frequency is equal to imaginary part of the system pole. In this way, this particular Laplace transform will have very important application in the control system analysis, right? So by seeing the roots of this denominator polynomial as a complex numbers, the first step you have to express in the partial fraction something like this. After that, determine the partial fraction coefficients k1, k2, k3 by comparing the coefficients. The next step is just rearrange the terms, and this is one answer. Another one is you just write down in terms of cos function. Once you got that cos function, what we can say that this overall response has two parts. One is exponentially decaying term, and it is having sinusoidal oscillations whose frequency is given by 2 radian per second. I hope you understand the concept. Now by using this particular concept, I will give you one question, and please try this problem for your practice. Now what is the question here? There is a differential equation given, x double dot plus 3x dot plus 6x is equal to 0, and initial conditions x of 0 is given 0, x dot of 0 is given 3. Okay. Now the question is, then find x of t. I just want everyone who are watching these videos, you try practice this problem just by applying the Laplace transform on both sides. I will give you answer for your cross verification. X of t is equal to 2 into root of 3 by 5 e power minus 1.5t into sine of root 15 by 2 into t. This is the answer. Okay. So everyone try to practice this, and this is for your verification. Okay. You try this question. Please try. So with this, I will sign off this video with another interesting concept. We'll meet in the next video. Thank you.